Okay, gives free energy. So this is in continuation of the second law of thermodynamics. Capital G is the symbol for gives free energy. G is a state function, so it will depend only on the initial and final states of the system. G is an extensive property, which means that G changes if the number of moles changes. The SI unit of G is joule because it's a form of energy, so the SI unit has to be joule. Change in Gibbs energy is denoted by delta G. Delta G. Delta means change. So change in Gibbs free energy is delta G. So what about the significance of delta G now? Why are we using this G? So it is going to be used for analyzing or assessing the spontaneity of a process. If something is spontaneous or not, that is what we are going to check using delta G. Spontaneous means what? A process which will happen on its own without any continuous external support. So if I want to find out about a particular process, that is whether it will happen on its own or not, then I need to calculate delta G and then predict its spontaneity. So if we calculate delta G of the system, then it is sufficient for us to understand the spontaneity of the process. So we don't need any other type of calculation for analyzing spontaneity. Once we know the value of delta G, we can understand. So delta G of the system will tell us if a process is spontaneous or not. So no calculation for the surroundings is required for assessing spontaneity. We just need to find out delta G of the system. If we know the delta G of the system, then we can figure out if the process is spontaneous or not. So some points about delta G. So the most important point is the first one that you see. Delta is
Sir,
negative.
what is the last line?
Delta G is negative for a spontaneous process. So the first point is delta G is negative for a spontaneous process. So if I know that delta G is negative for a particular chemical reaction or for a particular process, that means the process is spontaneous. I don't have to analyze any other parameter. I need not carry out calculations for surroundings. I just need to know delta G for the system. If delta G is negative, that means the process is spontaneous. So if delta G is positive, the process will be non-spontaneous. Delta G is zero at equilibrium. If I say that a process is at equilibrium, for example, if I talk about transition of this kind, if this is a reversible reaction, and if this reaction has reached equilibrium means the speed of the forward reaction is same as the speed of the backward reaction. So when both the forward and the backward reactions happen with the same speed, I say that the reaction is in equilibrium. At equilibrium, delta G is zero. There is no change in G, and so we say delta G is zero. Delta means change. So if something is constant, there is no change in it. And if there is no change, I say that the change is zero. So delta is zero. So at equilibrium, delta G is equal to zero. Similarly, if there is a change of phase, let's say I have melting of ice at 0 degrees Celsius. So again here, this is an example of equilibrium. So for any kind of phase transition, for any kind of phase transition at constant temperature and pressure, delta G is equal to zero. So melting of ice is an example. If I say that at 0 degrees Celsius, I have this process where ice and water are present in equilibrium with each other, then delta G for this process is equal to zero. So ice and water are present at 0 degrees Celsius. At 0 degrees Celsius, I will say that ice and water are in equilibrium with each other. So delta G is equal to 0 for this process at 0 degrees Celsius. It's important to mention the temperature. Okay. Similarly, if I show you this process, H2O liquid to H2O gas, that is vaporization of water, and if this process is occurring at 100 degrees Celsius. So at 100 degrees Celsius, liquid water is getting converted to steam. So again, I will say that delta G is equal to 0 for this process at 100 degrees Celsius. So for any phase change at constant temperature and pressure, the value of delta G is 0. And this minus of delta G is given a name. This is the name given. Maximum useful work. So if they ask you what is the value of maximum useful work that can be obtained from a system, you will say that it is equal to minus of delta G. So minus of delta G is what? It is maximum useful work that can be obtained from a system. मतलब वो सिस्टम मैक्सिमम कितना काम कर सकता है, कितना काम दे सकता है वो सिस्टम, मैक्सिमम वैल्यू दैट इज गिवन एज माइनस ऑफ डेल्टा जी. तो सिस्टम के अंदर क्या कैपेसिटी है काम करने की, इनडायरेक्टली दैट इज व्हाट वी आर ट्राइंग टू मेजर. So what is the maximum amount of work that a system can do? That is equal to minus of delta G. Let's look at the formula. So G is equal to H minus Ts. Mathematically, G is defined in this way. G is equal to H minus Ts. If I differentiate on both sides, then dg will be equal to dh minus tds minus s dt. Now, if temperature is constant for a process or a reaction, then dt will be zero because at constant temperature, temperature is not changing. That means dt is equal to zero. So this term will vanish. So dg will be equal to dh minus tds. Or delta G is equal to delta H minus T delta S. So this is a formula that we are supposed to learn. At constant temperature, delta G is equal to delta H minus T delta S. For a chemical reaction, also we can use the same formula. Delta G is equal to delta H minus T delta S. T means temperature. Delta S is change in entropy, which we have already done. And delta H is enthalpy change. If I consider an ideal gas undergoing an isothermal process, then this is a formula of delta G for that. So if they ask us what is the change in Gibbs energy for an ideal gas undergoing expansion or compression at constant temperature, then we can use this formula. N is the number of moles, R is 8.314, P is temperature in Kelvin, P2 is final pressure of the gas, and P1 is the initial pressure of the gas. Now, how to derive this? So we know that G is equal to H minus Ts, dG is equal to dH minus TdS at constant temperature, because what? The process isothermal. Isothermal means temperature is constant. If temperature is constant, dT will be zero. So we will obtain this dG is equal to dH minus TdS. Let this be equation 1. From the first law of thermodynamics, we know that du is equal to dq minus pdv. This is according to the first law of thermodynamics. du is equal to dq minus pdv. Now H is U plus PV. Mathematically, H is equal to U plus PV. Differentiating H on both sides, I'll get DH is equal to DU plus PdV plus VdP. Now, if I use equation 2, in equation 2, if you see it as this, du is equal to dq minus pdv. This can be adjusted and this can be written as du plus pdv equal to dq. So here I have this du plus pdv. This can be written as dq. So if I put dq, I'll get dh is equal to dq plus vdp. If I go back to equation 1, from here we can write dh is equal to dg plus tds. So dh is equal to dg plus tds. I can put dg plus tds here now. So in this equation, I put dh as dg plus tds. So I'll get this. Now from the definition of entropy, we know that ds is equal to dq upon t. ds is equal to dq upon t. So from here I can say that tds is equal to dq. So tds is same as dq. So I've put here dq as tds. So at last I'll obtain this. Now, if we integrate on both sides, we'll obtain this delta G is equal to integral of P1 to P2 VdP. Now, V for an ideal gas is nRT upon P, because we are assuming ideal gas in this case. So delta G is equal to nRT ln P2 by P1. This is for an ideal gas undergoing isothermal process. So we can write this. Ln can be converted to log by multiplying by 2.303. Okay, now this is an important table which is made for predicting spontaneity. If a chemical reaction is happening at a particular temperature, then whether it spontaneous or not. If I want it to happen at a particular temperature, then I should know whether the reaction is spontaneous or not. If I want to find out the spontaneity or the temperature at which the reaction becomes spontaneous, then I can use the value of delta G. So how do we arrive at this table? So let's see that. So for a chemical reaction, already I've told you, delta G is equal to delta H minus T delta S, where T is temperature. Now there are four different cases that are possible, because we don't know about this and we don't know about this. Now, if I see the sign of this and the sign of this, sign means positive or negative. So if I compare and then take a decision, then only I can predict the sign of delta G. Because for a spontaneous reaction, delta G has to be negative. delta G is negative for any spontaneous process. So let's see how we can arrive at different results based on the signs of delta H and delta S. So let's say we take an example of this, that is delta H is equal to plus X and delta S is equal to plus Y. Some arbitrary values have been taken. That means both delta H and delta S are positive in this case. Both delta H and delta S are positive. So what can we comment, or how do we assess the spontaneity, or what do we say about the spontaneity if delta H and delta S are positive? Let's see that. So now if delta H and delta S both are positive, I can say that delta G will be equal to plus X minus T into plus Y. This will be equal to X minus Ty. Now, if I want delta G to be negative, because I want the reaction to be spontaneous. So if delta G has to be negative, that means this entire thing has to be negative. So X minus Ty has to be negative. Now when can X minus Ty be negative? Because we know that X and Y are positive. So if X minus Ty has to be negative, that means the value of temperature should be high. If this value increases, then this entire term will become high, that is Yt or Ty. So if the value of temperature is quite high, then the value of Ty will also be quite high. And if Ty is quite high, then X minus Ty will become negative, because then we'll subtract a very high value from X. So I can conclude that temperature needs to be high for making delta G negative. In which case, in this case, when both delta H and delta S are positive. So if both delta H and delta S are positive, then the reaction will be spontaneous at high temperatures. Why high temperature? Because if temperature is high, then this Ty term will be high. And if Ty becomes very high, then X minus Ty will become negative. So if both delta H as well as delta S are positive, then delta G becomes negative at high temperatures. This is the conclusion. So that's what we have filled in the table. First one, delta H positive, delta S also positive. Delta G is what? Negative at high temperatures. And conclusion is the process is spontaneous at high temperatures. That is what we concluded. So this is how we can fill the table. Next, let's take a case where delta H is positive and delta S is negative. Now let's see what will happen. Delta H is positive and delta S is negative. So I'll put the value. Delta H is positive and delta S is negative. This will be X, this minus into minus will be plus, X plus Ty. X plus Ty. Now, if I want delta G to be negative, that's impossible in this case. Why? Because this particular thing can never be negative. It is X plus Ty. So there is no chance for this entire thing to become negative. So I can say that in this case, delta G will always be positive. Which means that if delta H is positive and delta S is negative, then delta G is always going to be positive, irrespective of the value of temperature. Because here, if you put low temperature, then also this is going to be positive. If you put a high value of temperature, then also the value of delta G is going to be positive. So, irrespective of the value of temperature, the value of delta G is always going to remain positive. If delta G is positive, process is non-spontaneous. Which means that the reaction will not happen at any temperature because delta G is positive. Let's go back to the table and see. Yes, so this is what it is. Delta H positive, delta S negative. Delta G is positive at all temperatures and process is non-spontaneous at all temperatures. That's what we concluded. Process is non-spontaneous at all temperatures. Okay. Now let's take a case where both are negative. Let's say delta H is negative and delta S is also negative. Now let's see what happens to delta G. So I'll put delta H as minus X and delta S is minus Y. So both delta H as well as delta S are negative. So minus X plus Ty, or I can say Ty minus X. So delta G is equal to Ty minus X. If I want delta G to be negative, now that means the value of T should be low. If the value of T is quite low, then only Yt will be very low. If Yt is low, then only Yt minus X will be a negative value. So if I want delta G to be negative, I can keep the value of temperature low. So if temperature is low here, then Ty will also be low. If Ty is low, then Ty minus X will be a negative value. So I can say that delta G will be negative when the temperature is low. So this is the conclusion. Delta G is negative at low temperatures. So process is spontaneous at low temperatures. And now the last case, where delta H is negative and delta S is positive. Let's look at this case. So delta H is minus X, delta S is plus Y. On solving this, I'll get minus X minus Ty. So this entire thing, if I see, compare this entire thing, this is always going to be a negative value. Minus X minus Ty, irrespective of the value of T, this entire thing is always going to be negative. Which means that whatever T I can keep, whatever t, whether it's a low value of t or a high value of t, this entire thing minus x minus ty is always going to remain negative. So delta G is negative at all temperatures. If delta G is negative at all temperatures, that means the process is spontaneous at all temperatures. So that is what we have written. Negative, positive, right? This is delta H and this is delta S. And hence delta G is negative at all temperatures. Conclusion is process is spontaneous at all temperatures. So these are the four cases. First case, both positive. Second case, delta H positive, delta S negative. Third case, delta H negative, delta S also negative. And last case, delta H negative, but delta S positive. So there are four cases. And accordingly, there are four different types of conclusion possible. Okay, if delta H is negative, then we say that there is a favorable change in enthalpy. So if they ask you, what is the meaning of favorable change in enthalpy? Favorable change in enthalpy means delta H is negative. Similarly, if they say that what is a favorable change in entropy? A favorable change in entropy means delta S is positive. Okay, let's look at a question now. So for a reaction at 298 Kelvin, delta H is given and delta S is also given. Above what temperature will the reaction become spontaneous? So we know that the formula of delta G is this. Delta G is equal to delta H minus T delta S. Put the values of delta H and delta S. Temperature is given as 298. Now they are asking above what temperature will the reaction become spontaneous? For spontaneity, we know that delta G should be negative. Negative means less than 0. So I can say that if delta G is less than 0, delta H should be less than T delta S. Delta H is given 100. Delta S is given as 0.05. Put the values. On solving this, I'll get T greater than 2000 Kelvin. So above 2000 Kelvin, the reaction will be spontaneous. So delta H is given as 100. Delta S is given as 0.05. And they're asking us above what temperature will the reaction become spontaneous. That is why we have used this equation, rather inequation, that is delta G is less than 0. Spontaneity, that means becomes spontaneous, that means delta G should be negative. So for spontaneous reaction, delta G is less than 0, negative means less than 0. And delta G is nothing but delta H minus T delta S. So delta H minus T delta S is less than 0, that is negative. And I've put the values, so I'll get T as greater than 2000 Kelvin. If T is greater than 2000 Kelvin, I'll say above 2000 Kelvin, the reaction will be spontaneous. This is the final conclusion. Above 2000 Kelvin, the reaction will be spontaneous. Okay. This was the first question. Above 2000 Kelvin, the reaction will be spontaneous. Next, this is the next question. What is the change in free energy when 2 moles of water at 100 degrees Celsius and 1 atm are converted to steam at 100 degrees Celsius? Now, change in free energy means what? Change in free energy means delta G. Change means delta. Free energy means G. Gibbs free energy. Either you can call it Gibbs free energy or you can call it free energy. So delta G is what we have to find out here. Now, what is the process? This is a process that is liquid water is getting converted to steam. And that too, it is mentioned that the temperature is 100 degrees Celsius and the pressure is 1 atm. So straight away we can say that since temperature is remaining same, that is at 100 degrees Celsius, temperature is remaining 100 degrees Celsius. At 100 degrees Celsius, liquid water is getting converted to steam. So delta G is 0 during change of phase. So I'll say that delta G is equal to 0. Similarly, if I say this, melting of ice at 0 degrees Celsius. For melting of ice at 0 degrees Celsius, then also I'll say that delta G is equal to 0. So for any kind of phase change occurring at a constant temperature and pressure, delta G is equal to 0. Okay. Carnot cycle. Now, heat is capital Q, work is capital W. And we're talking about a heat engine, which is a device that converts thermal energy to work and rejects some heat. Means what? It absorbs heat. A heat engine absorbs heat. That is Q is heat. and after absorbing heat, it will convert that heat partially to work. So some work will be done by it because it has absorbed the heat. And some portion of that heat will be rejected or released to the surroundings. Now, according to the second law of thermodynamics, heat cannot be converted completely to work. So if heat is absorbed by a device, only some amount of that heat will get converted to work, not the full amount of heat. Heat cannot be converted completely to work. So a portion of the heat will get converted to work, and the remaining portion of that heat will be rejected. This is according to the second law of thermodynamics. Now, based on this, we are trying to construct a device which will absorb heat and do some work and reject the remaining heat. Now, we want to see how much of work is done and how much of heat is rejected. For that, we have constructed a particular device called Carnot cycle or Carnot engine. And what is a Carnot engine comprising of? Let's understand that. So there is a source. Source means a thermal reservoir. A thermal reservoir is at a temperature T1. And there is a sink, which is again a thermal reservoir, which is at a temperature T2. And T1 is more than T2. So when heat is absorbed from source, because source is at a higher temperature, so when the device absorbs heat from the source, it will perform some work and then it will reject the remaining heat. So this is what the diagram is. HE is the heat engine. It absorbs Q1 heat from source and it rejects Q2 amount of heat to the sink. And W is the amount of work done by this heat engine. So this is a schematic diagram for us to understand what exactly is happening. So Q1 is the heat absorbed, Q2 is the heat released, and W is the amount of work done. Q1 is heat absorbed from a source. The thermal reservoir from which heat is absorbed is called source. And the thermal reservoir to which heat is rejected is called sink. Now, there are four processes which are happening one after the other. So these are the four processes. isothermal expansion, followed by adiabatic expansion, followed by isothermal compression, and then followed by adiabatic compression. These are the four processes which are happening. So a Carnot engine or a Carnot cycle comprises of four processes. So if they ask you which are the four processes in a Carnot engine, these are the four processes that happen in a Carnot cycle. Isothermal expansion followed by adiabatic expansion, followed by isothermal compression, and then followed by adiabatic compression. This is the graph. Pressure versus volume graph. So A to B, B to C, C to D, and then D to A. That is why this is called a cycle. So if you start from A, you come back to A. So what is A to B? A to B is isothermal expansion. What is B to C? B to C is adiabatic expansion. C to D is isothermal compression, and D to A is adiabatic compression. Okay, now mathematical expressions for each process are shown, like A to B, then for B to C, then for C to D, and then for D to A. So mathematical expressions are shown. You need not know that, you just need to know this particular thing. That is this, the results. The derivation is not required, so just learn the results. So what is the result? This entire thing that you see inside the box, this is what you have to learn. So this symbol, this is called eta. Eta. And eta stands for efficiency. So if they ask you what is the efficiency of a Carnot engine, so it is eta. And how do I find out the value of eta? Eta is equal to 1 minus T2 upon T1. T2 is the temperature of sink, T1 is the temperature of source. So 1 minus T2 upon T1. Also that is equal to 1 minus mod of Q2 upon mod of Q1. Q2 is the heat released, Q1 is the heat absorbed. Q2 is the heat released, Q1 is the heat absorbed. So eta is the efficiency of the engine. Let's look at a question. The efficiency of a Carnot engine is 1 upon 6. On decreasing the temperature of the sink by 65 Kelvin, the efficiency becomes 1 upon 3. Find the temperatures of the source and the sink. Okay. So efficiency of a Carnot engine is given to us. That is 1 upon 6. So the value of eta is 1 upon 6. So in the first case, the value of eta is 1 upon 6. In the second case, the value of eta is 1 upon 3. So there are two different values of eta given. What is happening in case 2? In case 2, the temperature of the sink has been decreased by 65 Kelvin. So initially, the efficiency is 1 upon 6. And after the temperature of the sink has been decreased by 65 Kelvin, the efficiency becomes 1 upon 3. So we can get two different equations in terms of temperatures and then solve them simultaneously. So let's say that T1 is the initial temperature of source and T2 is the temperature of sink. So this is for case 1. In case 1, the efficiency of Carnot engine is 1 upon 6. Formula for efficiency is 1 minus T2 upon T1. So I'll use that formula. And this is what I can say. 1 upon 6 is equal to 1 minus T2 upon T1. This is case 1, when the efficiency of the engine is 1 by 6. Case 2. On decreasing the temperature of the sink by 65 Kelvin, the efficiency becomes 1 by 3. So in the second case, the temperature of the sink has been decreased by 65 Kelvin. Hence, I can say that in case 2, the new temperature of the sink will be T2 minus 65, because decreased by 65 means it will be T2 minus 65. And so the new efficiency is 1 by 3. Now, solving these two equations simultaneously, we will get the values of T1 and T2. That's what we had been asked to calculate. The question wanted us to find out the values of temperatures. Hence, we have found out T1 and T2. So it was just an application of the formula for eta. So the only change that has been made is the change in temperature of the sink. That is a decrease. So the value of T2 has decreased by 65 Kelvin. Hence, the temperature of the sink now in case 2 is T2 minus 65. So solving these two equations simultaneously, we'll get T1 and T2.